has joined Department of Chemistry from. She's a full-time professor from 12th August of 2020 to till date. She has her research interests are solar photocatalytic water splitting and hydrogen production, solar photocatalytic CO2 reduction, solar photocatalytic degradation and mineralization of organic pollutant and solar cells. She supervised 12 PhD and 8 MPhil student has awarded degree. She is a recognized research guide in chemistry as well as environmental science. So her present group is having 2 postdoc student and 4 PhD student. She has attracted funds of 1.5 crore from various funding agencies like DST, BRNS, DAE, ISRO, UGC, BCOD, UOP, etc. She has successfully accomplished 10 research projects and 3 projects are ongoing. She has visited USA during May 23, June 2nd, 2014 and presented research paper on preparation and characterization of multi-walled CNTs, TiO2 nanocomposites for enhanced photocatalytic degradation. She is a recipient of distinguished awards, ICCAS Bronze Medal, and have been honored by Indian Association of Solid State Chemists and Allied Chemists in International Conference of Futuristic Material and Emerging Trends in Forensic and Life Sciences, ICFM 2015, organized by ICCAS and RTMNU for distinguished research contribution and achievement in material science. So her teaching she is involved in teaching to MSc, MPhil, and PhD students. So I would request Dr. Pragati Thakur to start her lecture on photocatalytic nanomaterials for their application in energy and environment. Thank you, ma'am. Thank you.
Yeah, thank you, Priyanka, for very nice introduction. So I will directly go to the presentation. I hope you are able to see the presentation. Priyanka?
Yes, ma'am, we are able to see your presentation.
Yeah. Okay, so first of all, I would like to thank the organizers from CMAT who have organized this invited talk and guest lecture under the training program, Creation of R&D Culture in Electronic Materials among SC, ST and women students in Maharashtra through Ministry of Electronics and Information Technology. And it is being organized by CMAT. And I would like to talk today on my research topic, which is on photocatalytic nanomaterials and their applications in energy and environment. So as first of all, going to the presentation as such, I would like to just highlight the outline of the presentation. Like some very few key terms would be talked, and then with the background, then the photocatalytic degradation of pollutants I will talk on, then on photocatalytic hydrogen evolution, which we are regularly doing in our laboratory, then highlights of the work which has been carried out, and some take-home message and the references. So typically, like in the title also, we do have two terms, that is photocatalysis and nanomaterials. Why I'm trying to just read out the key terms over here, because I know that the audience is undergraduate and postgraduate students, and they are from the rural areas. So I would like to just mention here what a photocatalysis in chemistry. Typically, it is the acceleration of photoreaction in the presence of a catalyst. So I hope all of you know what do you mean by a catalyst. And in photogenerated catalysis, the photocatalytic activity typically depends on the ability of the catalyst to create electron-hole pair. Okay. Typically, the photocatalyst what we use, they are the semiconductors, and the photocatalytic activity depends on the generation or the creation of electron-hole pairs, which ultimately generate free radicals, which are able to undergo secondary reactions. And nanomaterials, as we all know that nanomaterials, they are materials of which they have size, at least one dimension is between 1 to 100 nanometer. And not only that, these materials have unique optical, electronic, thermophysical, or mechanical properties. Okay, so typically you may come across, when you talk about nanomaterials, then you can come across with zero-dimensional nanomaterials. They are typically the dimension in all the size in all the dimension is in a nano scale. So they are typically nanoparticles. And yeah, one-dimensional nanomaterials, typically they are the nanotubes. So one of the dimensions is uh, other than the nanoscale. So nanotubes, nanorods, nanowires are one-dimensional nanomaterials. When you talk about two-dimensional nanomaterials, so you typically talk about nanofilms, nanolayers, nanocoatings, and as such. And fourth one is the three-dimensional nanomaterials, typically bulk powders, dispersions of nanoparticles, bundles of nanowires, and so on. So these are the key terms. So coming to the, So coming to the area in which we are studying. So the mission statement for our research group is the development of simple strategies towards clean energy and environment via nanophotocatalyst and solar energy. So we all know that energy and environment are the two major challenges before the whole globe as such. And Department of Science and Technology, through its various initiatives such as Nanomission, Water Technology Initiative, Clean Energy Initiative, have encouraged India time to time to develop critical mass of researchers to meet the requirement of R&D professional for clean energy and environment. So aligning with these initiatives, actually, we started our research, and we are now synthesizing regularly and characterizing various photocatalytic nanomaterials for their applications in photocatalytic degradation of pollutants and photocatalytic hydrogen production. We are also in CO2 reduction applications as well. So yes, nanomaterials and solar power. So when we are talking about nanomaterials, and when we are talking about photocatalytic nanomaterials, then the one thing which is very prominently come to our mind is the solar power. How we can use this inexhaustible source, renewable source of energy to accomplish various applications which will ease our life. Okay, so typically, I would be talking on these two applications, that is photocatalytic hydrogen evolution and photocatalytic degradation of pollutants over here. So as you know all, in today's scenario of rapid industrialization, the problem of unsafe water, its consumption, and thereafter effects have become a great challenge before research community, isn't it? So to get safe drinking water in adequate amount is a birthright of every human being. Therefore, the ultimate challenge and goal of any researcher working in this area of water remediation would be to develop simple strategies and to apply them for large-scale technical applications. So, this goal seems to be, to achieve this goal seems to be difficult, isn't it? If we ignore the technology transfer problem, perpetuating the widening gap between the academic advocation and industrial application. A recent search in scientific literature, typically over 8,000 articles since 2000 on the topic of photocatalytic water treatment, still reflects optimism to reduce this gap between expectation and accomplishment. But typically performed at bench scale. This bench scale means at lab scale. This photocatalytic water treatment studies tend to overpresent the opportunities and underpresent the limitations demonstrated by the technology when applied in the field, in the actual field, when we apply this. Okay, thus one need to critically analyze. So we need to critically analyze the fundamental problems or the fundamental roadblocks in PWT, that is photocatalytic water treatment, that are preventing the transfer of research to practice. And the highlighting challenges are the low photoconversion efficiencies of the traditionally used benchmark photocatalyst, and further the reactor or the system engineering aspects. So here I would like to share some of our prominent works carried out during last 10 years focusing these typical challenges. Then, apart from the ever-burning topic of wastewater treatment, the challenge of green fuel production is attracting attention of researchers all over the globe. As you know, global warming, climate change are the most eminent threats for the 21st century in view of the increased energy demand due to modern civilization in recent years. Okay, our lifestyle is energy intensive. It has become very energy intensive. So the traditional energy sources what we are using, like such as fossil fuels, which are not they are not sustainable. Okay, and they would leave an energy gap of typically 14 terawatt by the year 2050, but also would contribute. They will not only leave that energy gap, but they will also contribute huge amount of anthropogenic CO2 emission to the atmosphere, leading to environmental crisis. Okay, we know that due to the increase in the CO2 emission, the various global warming and climate change, this environmental problems are coming up. So to fill this energy gap, solar energy is the only inexhaustive renewable potential energy source which can be effectively converted to the environmentally friendly chemical energy via photocatalytic hydrogen evolution from easily available precursor water. You can just use precursor as a water. Further, the CO2 emitted into the environment by traditional polluting energy sources can also be reduced. Okay, so instead of using the fossil fuels, we can have an alternative where you can use solar power, that is a renewable energy source, and you can achieve two things. Fine. Thus, the science and technology interventions through the indigenous efforts to develop simple strategies toward clean energy and environment via nano photocatalyst and solar energy is an urgent need of time. I hope you agree with this. So what happens? Like first, okay, let me go to the next slide. Excuse me. Yes. Are you able to see the next slide? Priyanka, can you hear me?
Slide has changed, ma'am. Yes.
Slide has changed. Okay, because I thought it is whether it is changing or not.
No,
so
no.
it has been
You can
changed.
see the
Okay,
next
okay,
slide.
okay,
Yes,
okay.
ma'am.
So we will talk in a little bit about, first of all, photocatalytic degradation of pollutants. So the basic principle of photocatalytic degradation of pollutants using semiconductors is when you irradiate any photocatalyst with energy greater than or equal to the band gap energy of the photocatalyst, then there is a generation of electron and hole pairs. Okay, so the electrons are excited into the conduction band and the electron vacancy, that is holes, are generated into the or they are there in the valence band. Okay, and in an aerated suspension, if you take an aerated suspension, means if you have carry out the reaction, typically you carry out this reaction in a reactor and with water as a solvent, and you add some pollutant, some synthetic pollutant or some real wastewater into that, and then you aerate this suspension by adding your photocatalyst. So when you irradiate that photocatalyst, what happens? There is a generation of electron-hole pairs. Electrons are in the conduction band, and holes are left in the holes. That is the deficiency of electrons in the valence band. So what happens? Either the electron and holes, they will combine together, and there will be no photochemistry done if they are not exploited or they are not extracted separately. Okay, so what we have to do, we have to extract the electrons separately and the holes separately. So what we do, one of the ways is that in an aerated suspension, that oxygen scavenges the electrons from the conduction band, and in this process they prolong the lifetime of holes as well. So what happens, this electrons, they produce superoxide radicals, and these holes are either absorbed, and they absorb the water, or they directly oxidize the organic pollutant. And there is a generation of hydroxyl radicals which have got very high oxidation potential. So ultimately what happens, that any pollutant is degraded or mineralized into water and CO2 and some mineral acids. Okay, so the organic pollutant goes into this, and the advantage of this PDP, that is the photocatalytic degradation of pollutants, is that there is a real destruction of pollutant rather than a simple transfer on a substrate. So if you see the other ways of pollution abatement, or the other ways like adsorption on activated carbon and other things, so there what happens, we are just taking the pollution load from one state to the another state. The pollutants are adsorbed on activated carbon or adsorbents, and there is only shift of the pollution from liquid state to the solid state. But this is not the case when you talk about photocatalytic degradation of pollutants. Here you are ultimately going to get water and CO2 which are harmless. Then the other beauty of this photocatalytic degradation process is that the degradation of pollutants, you can carry out this reaction at ambient temperature and pressure, and they can build with easily available materials by means of well-known techniques. Okay, so the photocatalyst can be easily prepared or they can be synthesized, and this process is economical, and the energy consumption is also very low. And this is non-selective, means you can adapt this procedure for large range of pollutants, like from VOCs to bacteria to mold, so many kind of pollutants you can degrade or mineralize with this typical photocatalytic degradation process. So we have seen here that for this photocatalytic degradation, the material what we require is some typical semiconductor. So we have seen here this example of benchmark traditional photocatalyst is TiO2. Why? Because these are the prerequisites of photocatalyst for PDP. What are they? It should be photoactive, photostable, biologically and chemically it should be inert, it should be non-toxic and inexpensive, it should have favorable band gap, and it should have high oxidation potential. Okay, so as this TiO2 is having all these advantages, that is used as a benchmark photocatalyst traditionally, but still it has got some challenges. So what are the challenges? Before TiO2 photocatalysis towards developed technology for wastewater treatment, because we are not only concerned about the things at lab level or pilot level, but we want the technology transfer also. So we need to check that what are the drawbacks in that system. So the first drawback for TiO2 photocatalysis is electron hole recombination. Okay, as we have seen while seeing the mechanism also, the electron and holes which are generated, they recombine very quickly in nanoseconds or picoseconds like that, and they are not available for the further reactions, oxidation reduction reactions, they are not available. So the efficiency of the photocatalyst is not very high. The second drawback of this is TiO2 is active only in near UV region. The band gap of TiO2 typically it is 3.3 to 3.2 electron volt, depending upon whether it is rutile or anatase. So typically anatase is the most photoactive phase. So, but both these are active in UV region. Okay, and then the why and we want to go to the visible region. Why we want to go to the visible region? Why we want to make it active in the visible region? Because in the solar spectrum, typically 45 to 50% of the region is of visible light, and only 4 to 5% comprises of UV region. So we want either some photocatalysis which is active and having all the prerequisites for efficient photocatalytic degradation in visible light. Then the other drawback of this is that limited absorption of organic pollutants on the surface of the TiO2. Okay, so we have to use some templates, or we have to create or design some such materials which will increase the absorption of organic pollutants on the surface of the TiO2. Fine. And the other challenge is TiO2 in suspension mode is not suitable for large scale technical applications. Fine, because here we are using in the system the TiO2 in a powder form, and it is highly dispersed state, and when we have to remove it from the system, it requires filters, and that adds up to the overall cost of the reactor and everything. It becomes cost intensive. Okay, so it is not suitable in suspension mode for large scale technical applications. So we need to go for some other systems. So what are the strategies? Then what should we do? Other strategies for the development of highly enhanced photocatalysis system for wastewater treatment. So we can go with all of these or some of these or one of these strategies, like design and development of various types of photoreactors. The photoreactor, that is the design, that engineering also matters. Then combining TiO2 photocatalysts with other AOPs, and what we typically do when we work in the synthesis of photocatalytic nanomaterials is that modifications of this TiO2 surface by composite formation or by formation of some heterostructures. So in that, people are working, and I have worked a lot on the modification of TiO2 by modifying with metals such as platinum, palladium, silver, and etc. Then they are preparing some heterostructures with narrow band gap semiconductors like CDS, SB2S3, ZNO, etc. Because here narrow band gap semiconductors means they will be active in a visible light. They act as a sensitizers over there, and when you add or when you dope or when you decorate this TiO2 surface with platinum or any other metallic nanoparticles or metals, then what happens? They are helping us in preventing the electron hole recombination, and also the absorption range of the photocatalyst also extended to the visible light. So it all depends upon how you are preparing it, what kind of a heterostructure or what kind of decoration or what kind of doping you are going to achieve. So these are typically the ways of doing it. And next is the modification of TiO2 by some carbon materials, or preparing some composites with carbon materials like activated carbon, carbon nanotubes, graphene. So one of the advantages, as you see, as they are the carbon materials, that the surface area is increased. So there is the increased absorption of organic pollutants on the surface, and then also they act as a good electron sink. So that is one another advantage of it. When I'm trying to go to the next slide, it is getting stuck. I really don't know. So let me escape. I'm not able. Yeah, I'm not able.
You are stuck on one slide only.
Yeah, so that is, I'm trying from my side. Last time also it happened the same thing. Let me check it.
Yes, ma'am.
Yeah, just wait a minute. Okay, so why it happens like that? I'm also very much surprised today.
It's okay that if it is not working in presentation mode.
Yeah, let me check. Yeah.
Yeah, now
Yes.
it's coming. Yes.
Yeah, so now we will talk something about the photocatalytic hydrogen evolution. Okay, in a typical photocatalytic hydrogen evolution or hydrogen production process, upon light irradiation with energy equal to or greater than the band gap energy of the semiconductor, electron and holes are created, as we have seen in case of photocatalytic degradation. The mechanism is is going to be the same initially, and the electrons and holes are created in valence band and conduction band respectively. The photogenerated electron hole migrate to the surface of the photocatalyst. They either migrate to the surface of the photocatalyst, and H plus ions are reduced into molecular. The H plus ions are reduced into molecular hydrogen by electrons in the conduction band, and water is oxidized into O2 by the holes in the valence band. It is necessary. Again, what are the prerequisites for this uh, photocatalytic hydrogen production? For that, what are the prerequisites for photocatalyst are the conduction band minimum of the semiconductor must be more negative than the redox potential of H plus to H2, and valence band maximum must be more positive than the redox potential of water oxidation to O2. So here you can see some of the photocatalysts are shown here with their band edge positions. Okay, so typically you can see that this TiO2. We have already seen the what are the other advantages of TiO2 as a best photocatalyst, as it is photostable, photoactive, and it is inexpensive, it is a environmentally friendly, and so many things are there. So, and again, the band edge positions, they are properly arranged. Okay, so as we have seen, the conduction band of semiconductor conductor must be more negative than the redox potential of H plus to H2. So you can see that the bandage positions are proper here, and some other semiconductors are also there. One more is that this graphitic carbon nitride, this is a carbon material again. So you can see this, such kind of material you have to choose. So typically the other materials which are having their bandage position not suitable, they might not be useful for this photocatalytic hydrogen production. I will not say water splitting, but hydrogen production. Then the second prerequisite is that the semiconductor band gap must be or must exceed 1.23 electron volt. So this, okay, so this should be, this is the theoretical value. So this should be more than 1.23 electron volt. They must have corrosion and photocorrosion resistance, and obviously low cost of manufacturing should be there. Again, I am trying to go to the next slide. Let me see how I can go that.
Ma'am, we are unable to see the next slide.
Yeah. I am also trying here. This is surprising for me that why this is happening, and this is for the first time I am having this kind of a issue.
Yes, ma'am.
Let me check. I think this is the issue from my side. Yeah, we have gone to the next slide. Thanks. So shall I keep it in this mode? Because this is going fast. Or shall I put it in a presentation mode, Priyanka?
Yes, ma'am, you can put it in this mode.
This
No
mode
problem.
only, na? Yeah.
It will be better because
Yeah.
every time we stuck, na.
Yes. So we have seen last slide also we have seen what are the challenges of TiO2 for photocatalytic degradation, and in PHE, that is photocatalytic hydrogen evolution, again the same limitations are there, that the wide band gap of TiO2 which limits its application in the visible light, and even in the presence of sacrificial agents, efficiency of TiO2 is low due to the fast charge carrier recombination. Will you please put on your mute mode? Excuse me. Will you please put on? Kindly keep yourself on a mute mode. Yeah, so strategies to meet these challenges are, you can have some metal modified TiO2. You can modify the TiO2 by non-metals. Then you can modify or prepare carbon material based TiO2. You can also have some metal, non-metal, carbon material based photocatalyst. You can have some ternary composites and semiconductor coupled TiO2 also you can have. So here in this figure, this is very interesting figure. This is a schematic representation of the important steps in the photocatalytic water splitting using the semiconductors. As you can see that this is a pathway 1 where there is electron hole recombination in the bulk, and this is the pathway 2, exciton migration to the surface. Exciton is the pair, electron hole pair, which is generated, that is called as exciton. So they migrate to the surface, and here this is a pathway 3, the surface electron hole recombination. So this at the surface also the electron hole recombination is there, and they will dissipate energy, heat, so there will be no photochemistry there. And the fourth pathway, exciton transfer to reactant. So we are more interested in this exciton transfer to the reactant, so that there will be conversion of H plus to molecular hydrogen. So let me go to the next slide. So we have in our lab tried to study some of the modifications of TiO2, which I would like to share with you very briefly. So you will get an idea like what different photocatalytic materials can be used, and what strategy you can use to develop some such materials which would increase the photocatalytic activity of the particular system in a solar light or sunlight. Okay, so here I would like to share the result of platinum RGO TiO2 ternary composite for photocatalytic hydrogen evolution. So we all know that the platinum is a very best co-catalyst for photocatalytic hydrogen evolution because of its very high work function, and it is a good electron sink. So it creates a Schottky barrier when it is there is a formation of TiO2 and platinum, or when you decorate platinum with TiO2, so the platinum takes away the electrons, and the electrons are used for the reduction of H plus to H2. Okay, but the thing which is not favorable here is platinum is a noble metal and it's very costly. Okay, so we need to see some other strategies or some remedies which would decrease the percentage of platinum in the system, because till now the highest efficiency shown by platinum tier 2 system, which is supposed to be the base system, is 22.6%. Quantum efficiency has been shown with a platinum percent of 2.5% in the platinum tier 2 composite. Okay, so 2.58% is very high percent. So we focused our research that can we decrease this platinum percent by some strategy. Then we thought that as RGO is recently being used as a very efficient material, so we have incorporated here reduced graphene oxide, which acts here as a very good electron sink, and also it has been shown that it has increased light absorption in the visible light. This people have shown that the studies, and like what we thought, we can prepare a ternary composite of TiO2 with platinum and RGO, thereby reducing the percentage of platinum in the system, but still getting the highest or higher efficiency. So here we have used 1% platinum and 10% of RGO we have added here in this ternary composite, and we could find out that the efficiency or the photocatalytic hydrogen evolution was found to be typically around 2000 micromole per gram. So that was that was very high as compared to TiO2, because TiO2 simply gives around 100 micromole per gram. And when we use this platinum and RGO as a composite, as a ternary composite with TiO2, then we found that it has increased to 2000 micromole per gram. So that is too much hike in the efficiency. So, but just mere lowering the percentage of platinum in the system will not be that practical, as we want to go to a metal-free system. Okay, we don't want any metal to be there, so we want a metal-free system. So when going to that metal-free system, what we thought, we can use the graphitic carbon nitride system. It is a non-metallic pi conjugated polymeric material, graphitic, and it has got a band gap of 2.7 electron volt, and the band conduction band is also favorable for the reduction of H plus to H2. So we thought, why not to use that graphitic carbon nitride and make a composite of it with TiO2. I am here writing this P25 TiO2. P25 is a commercial TiO2 which is commercially available. It is a combination of two phases, rutile and anatase. Rutile phase is 20%, anatase is 80%. So there also it has got an advantage that electron hole recombination is prevented in this particular P25 TiO2. And in addition to that, we have also doped phosphorus into that graphitic carbon nitride. So what system we have prepared? A completely metal-free system where we have doped phosphorus into graphitic carbon nitride, and then we have made a composite of it with TiO2. So this figure is showing you this is a graphitic carbon nitride. When you dope it with phosphorus, then there is a change in the hybridization, and you can see the change in the color as well. And this is the DRS spectrum, which shows that this graph, this absorbance shows that the absorbance has been increased more to the visible region. Okay, if you compare this is P25, this is graphitic carbon nitride, this is phosphorus graphitic carbon nitride, and then we have also optimized the percentage of graphitic nitride and phosphorus doped graphitic nitride in this P25 TiO2. Okay, so what we have achieved, you may not understand it to that extent, but try to understand that when we dope a phosphorus into the graphitic carbon nitride system, what happens? It is extending the light absorbance in the visible region, what we actually wanted. Okay, and is also increasing the like when you prepare a graphite carbon nitride P25 composite, then it forms a type 2 heterostructure. Type 2 heterostructure means the electron, when you excite the photocatalyst, the electron grows from the valence band to the conduction band, and from the conduction band of one semiconductor, it goes to the conduction band of another semiconductor. The positions of these conduction bands of this graphite carbon nitride and P25 are as such that there is a migration of this electron from the conduction band of graphite carbon nitride to the P25, and thereby there is a separation of the charges, or the electron hole recombination is prevented here, because that is one of our focus, because we want to increase the efficiency of a photocatalyst, so we need to focus on that. So both the things we have achieved here, we have increased the light absorption into the visible region, and we have again decreased the electron hole recombination. Thereby the efficiency has increased, typically 40-fold, 50-fold the efficiency has been increased. Please keep yourself on a mute mode. And these are the some characterization techniques I have shown, that is the TM, ACM, that is that gives about the morphology, that gives information about the morphology of the catalyst. So these are some cyclic voltammetry voltammograms here. So I will not go into much of the details of it. So I would just leave it here. What I want to say that with a proper planning, you can increase the efficiency of any photocatalyst, or you can design any photocatalyst as such, which will be able to harvest as much as solar light, and it will be economical also, and it will be practical also. So such a way you have to plan your work. And then also you can prepare some photocatalyst composites. Like here we have prepared cuprous oxide P25 photocatalyst. It forms a PN junction over here, and that also helps in the electron hole recombination, that prevents the electron hole recombination, such that the efficiency of the catalyst is increased to 100 and 125 fold more as compared to just P25 TiO2. So here we have shown the mechanism, and we have carried out the recycled use of the photocatalyst. So up to 4th cycle, we have seen that there is not much decrease in the efficiency of the photocatalyst, and the composites prepared are very good composites we have prepared. Then we have synthesized further some nanowire TiO2. You can see these nanowires are there, and they form a like ball like structure, as you can, or flower like structure, as you can see. And this is, as you can see, this is the ACM image of that NWT. So you can see that it is so very porous. It is so very porous that it has shown typically 100 times more efficiency than the commercially available TiO2. This work has been carried out. This manuscript is under preparation. Here we have shown that how you can use the platinum, because platinum, as it has got a very high work function, so it is best co-catalyst for photocatalytic hydrogen evolution. So you cannot avoid that. So we have used platinum, but we have used very less percentage of platinum over here, and we have used a non-metal, that is sulfur, which will extend the absorption or the capacity of the photocatalyst in the visible region. And platinum will act as a electron sink. So both these limitations of TiO2 can be overcome in this composite. So that is also giving very good results, and this manuscript is also under. So what are the highlights of the work? So if you can see, I have summarized this various what we have synthesized along with the hydrogen evolution values of that. So this is for P25, that is a commercial TiO2. It is just 99 micromole per gram. Then synthesized TiO2, it has been increased to 444. That is a very good sign. And then graphite carbon nitride, it is just 40%. Then cuprous oxide, and all these values are given over here. And the base synthesized heterostructures, what we have got, I have enlisted over here. So we have prepared platinum RgO2, we have prepared two semiconductor heterostructure, then we have prepared this ternary composite. So here you can see then as compared to platinum RgO2, this has increased. And again, this phosphorus dope graphitic carbonate has given increased efficiency. Then copper NWT, that is the nanowire TiO2, which is highly porous. It has again increased the hydrogen evolution capacity. Then platinum NWT has again increased. You can see the difference because it is, we are having here platinum, which is the best co-catalyst till now. And then we have used like one metal, both metals like Ag and copper, that has further used, and the base system what we have achieved in our lab. And I think I have done some survey also. So this is a very good result what we have observed, this platinum sulfur TiO2. Let me go to the other slide. Yeah. So I think I have left very less time with us. I will quickly go through the some of the results what we have observed for photocatalytic degradation of pollutants. So here also for this to make any catalyst like transferable to the technology, we have to see about the cost of it. So here again we have tried a metal-free photocatalyst with C.TiO2. Okay, we have prepared here carbon dot RgO TiO2 ternary composite. Okay, which I have already explained one of the system with RgO TiO2. So same kind of mechanism also goes here. And carbon dots have their other advantage. They are used as they act as for upconverted photoluminescence, so that property is also used. So you can see that what this kind of judgments or what this kind of materials they do, they increase the efficiency in the visible light, they are economical, and they can be repeatedly used. So these three things should be focused over there. Then this is the synthesis and photocatalytic applications of AgTiO to AC. So instead of other carbon materials, we have used simply activated carbon. And here again, we have used this TMAC. This is a titanium coated magnetic activated carbon. So what we have studied, what we have done, we have prepared some magnetic nanoparticles, or where we have used TiO2, where we have used Fe2O3, then we have used activated carbon. So that photocatalyst can be easily recycled. That was one of the focus of this work. They can be easily recycled and reused. Then we have prepared synthesis of TiO2 with MWCNT composites. These are the multi-walled carbon nanotubes. They have also given fantastic results over there. And here we have tried to degrade the various pollutants, not only dyes, but phenols, paranitrophenols, cresols, and so many other. So what we have shown here, that this is not a selective method. This typically degrades all kind of pollutants. Okay, so here are some of the results of this AgRgO-TiO2. These are the similar kind of systems. I just want to show that what different systems you can prepare on your own. Then RgO-ZnO. ZnO is also a competitive photocatalyst as compared to your TiO2. So some of the results are shown here. The UV visible DRAs, then the Kubelka function plot, which calculates the band gap of the photocatalyst. And then some other studies like graphitic carbonated AgZnO or platinum WO3 graphitic carbonated composites. So one thing is very important. You see that it is not only application, but the proper synthesis of material and proper characterization is also very important. So you have to take care of that as well. And these are some other systems where we have used synthesized sp2s3TiO2 composite, ZnO-CDS composites, where this CDS acts as a sensitizer. Yeah, and while doing all this research, we have developed different designs, or we have done some modifications. So this is, initially we were using this immersion well photoreactor. So where we could find that the light intensity, if we increase the light intensity to some more extent, then that would be good for us. So we have modified the design. And then here we have used a multi-lamp photoreactor. So here 4 lamps we have used, 4 UV lamps we have used, and the reactor is kept in between. Okay, here we have used solar continuous photoreactor. So this is a solar continuous photoreactor. This is a batch reactor. This is a continuous reactor. We have used a peristaltic pump, and this is kept in a sunlight. And this tube that carries this pollutant, and then again it goes back into the reactor or the beaker where we have kept the original solution. And this is the solar continuous photoreactor. And this is the one which we, this is a solar simulator. Which mimics the sunlight. Okay, so we have all visible light and UV light and all that, and we irradiate it. So this is that development of the reactor and the design. So highlight of this photocatalytic degradation work, like we have synthesized over 50 photocatalysts till now. We have studied almost 12 to 15 different pollutants. In that we have used various phenols, various dyes, and some pharmaceutical pollutants also, like propanol, atenolol, which are the beta blockers. And we have developed in this overall work, we have developed various photoreactors, and we have also tried to treat the real wastewater. The typically dye industry effluent we have tried, then distillery spent wash also we have tried, and then laundry effluent. But when you want to go for a real industrial wastewater, you cannot directly apply this photocatalytic treatment to it. Okay, so we need to carry out some initial primary and secondary treatment methods, and then only we can go at the trace level for this photocatalytic treatment option. So the take home message is that the whole work what I shared, what we have carried out in our lab, so it highlights that with systematic approach, rational fabrication of high efficient composite, just a minute. High efficient composite heterostructure to harvest renewable solar energy for enhanced photocatalytic hydrogen evolution and photocatalytic mineralization of the pollutant can be achieved. So you have to have a proper systematic approach for the fabrication of a rational design of a photocatalyst. Not any material you can just mix and try to prepare something. Okay, so there has to be some logic, there has to be some science involved in it. And the one obviously a very obvious take home message is that do as much as tree plantation as you can. Don't waste water. Okay, otherwise you will have to use wastewater. Are you getting it? And try to use minimum, or try to use minimum energy intensive lifestyle. Okay, so as much as simple life you can live, that you have to prefer, because that is going to cost to our next generation. Fine. These are some of the references which I have used for this. And definitely here I would like to acknowledge Dr. Bharat Kale sir, Director General, Center for Materials for Electronics Technology, CMET Pune, and Dr. Sunit Rane sir for giving me this opportunity to share my views and my work with you all people. And I wish you all a very best in your future endeavors. Thank you very much.
Thank you so much, ma'am, for such a nice lecture. The session is open for question and answer. If you have any question, you put it in chat box or unmute yourself. If anyone have questions, please do ask in chat box, or you can unmute yourself. And we'll wait for 5 more minutes for questions.
Yes, no issues, no issues. You can.
We'll conclude.
But I hope I have finished in it time.
Yes, ma'am. Yes, ma'am. Absolutely in time. One new message is there. For visible radiation, can we use LED light?
Yeah, typically what wavelength you want. So accordingly, you can plan and you can use LED lights.
So basically, you need to check the wavelength and the intensity of the LED light, right, ma'am?
Yes, yes.
Thank you, sir. Thank you, ma'am. Anybody else?
Yes. Is there any question? I would be happy to answer.
Okay,
Priyanka?
I think there are no questions, no more questions. So we'll go for last the conclusion part. On behalf of CIMED Pune and the project team, on behalf of CIMED Pune and the project team, I am here to spell out the words of thanks to all the faculties and the students for joining in the webinar. And I am very humbled and honored to be here to give vote of thanks to my mentor, Dr. Pragati Thakur ma'am, for such an distinguished and intellectually stimulating session. Thank you so much, ma'am.
Thank you, Priyanka. Thank you very much for inviting me and giving me an opportunity to share my work with you all. Thank you.